Hello everyone, this is Professor Dr. Daniel Stein. I'm working with Professor Mazzella, putting ET110 Lab 7 online. So this will be found in Blackboard. What you're looking at now is a screen, and this is the document that you downloaded. It's a Word document. You'll be able to type your name. In any one of the yellow spaces, you can add the information. So you're going to download this Word document. You're going to complete your lab. And then the lab has parts as you go through the document that need to be filled in. And then there's going to be an answer sheet at the bottom. You'll note you have to put your name on the answer sheet as well. Okay, you're going to submit the whole thing via Blackboard to Professor Mazzella when you're done. Okay, so we're ready to get started. He's going to explain the highlights. This is Professor Mazzella, and I'm going to make it a little bit larger so that he'll be able to see this, and you'll be able to see it better. And this is what are the highlights of this Lab 7. Thank you. Take it away, Bob.
Hi class, this is Professor Mazzella, and today we're going to talk about Lab 7, which is Kirchhoff's current law. To demonstrate KCL, Kirchhoff's current law, we can visualize water flowing through a hose that splits into two outputs, as shown in the diagram. The water flow will split and flow equally out of each opening if the two output lines are the same size. Okay. The sum of the two output flows must equal the input flow. So that's the idea with visualizing that. Two outputs will equal the input. Now, if one of those outlets is restricted, more water will flow from the other outlet. That makes sense. I think you've seen such a thing happen with the garden hose. But the total output will always be equal to the sum of the inputs. Okay, that kind of is something you can visualize, and we're going to convert this into the discussion with electricity by looking at page 9, figure 1, A, B, and C. Okay, in figure 7.1, A and B, we show two different current flow paths, and in figure 7.1C, we combine the two flows compare the sum of the total flow to the individual flows. Note on this here is that if we connect the battery to the circuit only, if we build a circuit, we connect the battery only while we're reading the meter, as leaving it connected will discharge the battery, lowering the output voltage, and it will disturb the reading's accuracy. Okay, so that's a little project that you can do. On page 19, figure 7.2, we show a fan as one of the loads on the source. In other words, when we did this lab in the class, we supplied you with a little fan that you would also hook up to your battery or voltage source. And it would show that electricity that goes through a fan flows the same way as that to a resistor. We could have also substituted for one of the resistors a light bulb, maybe an electric heater, or a bell, or a horn, or something that used electricity. The idea was to show that the two paths, one would be a resistor, the other could be any other electrical load, and I mentioned what they could be. In the case of the fan, if we did use that, you would see an increase in the current of the fan as you slow down the fan blades by pressing against the blades with your finger. In other words, an electric motor could vary the amount of current that it draws by the speed at which it's running. Whereas when you first would start the fan, the current would be higher. As the fan blade sped up, the current would go down. You could, again, simulate a slower fan by putting your finger against the hub of the blades, not in the blades, and that would show that the current would go up again. And therefore, that fan motor is not quite as linear as a resistor, because a lot happens depending upon the load on the electric motor. Okay, so this happens with electric motors as an example. If if you have an electric bicycle or a child's electric car. You might have seen that when the guy goes down a block, electric car. The motor will draw more amperage from the source as the car or bicycle is going uphill, and they actually change the charge the battery when going downhill. In other words, if you spin the electric motor, certain motors, faster than the voltage is supposed to drive them, we would actually recharge the battery. And you might have heard of this happening in today's electric cars. When stopping the car, you recharge your battery, and that process is called regenerative braking. So if you build that circuit, if you use your battery, you can get to see the currents. But I'd like you to build a circuit, take pictures of the circuit, and send it to me so I can see that you built the circuit properly, even though you may not have the supply to test it if the battery is gone, discharged. But I want to see that you can draw the circuit, wire the circuit, and try to make the proto board look like the schematic. Remember I spoke about that test. Well, I'll be looking for your responses. Thank you very much, and have a great day.
One last thing I wanted to share, thank you, Professor Mazzella, is that these videos are also available from Professor Mazzella's website. It's here. You can see when you download it, you hit Control-click, and you'll be able to go to Professor Mazzella's site, and you'll be able to see the different labs and the different videos. So you don't have to go back. If you want to review this, you don't have to go back into Blackboard. Okay. Thank you, everybody. I hope you enjoyed the presentation.